Okay, so basically, we go back to the example that we were completing last time. So and in particular, the idea was to calculate the element stiffness matrix. Okay, so we go and check again our system, which is basically composed only of one element. And basically, what we do to calculate the stiffness is to resort to the definition of the potential energy, elastic energy of the element Uij, which we define as we have already done many times as the integral over the length Lij of the element of what? Of the axial stiffness EA multiplied times the derivative of order 1 of the axial deformation-induced displacement W1 with respect to the undeformed coordinate in the axial direction x over bar 1, 0 squared. And this is the, let's say, the part associated to axial deformation. Then we have the flexural counterpart, which is the second order derivative of transverse deformation-induced displacement, always with respect to the same coordinate x1. I will put Ij on top of the square matrix just for the ease of notation, but in theory, everything should have Ij here on the, as a superscript. Okay, integrated in the x0. Okay. Now we have if you remember that the position of a point of the element Ij with respect to the body frame B1, B2 is Nij applied over QEI, which is the vector of the nodal coordinates of the overall body described with respect to the body frame. This could basically also partitioned into a reference part, y, plus a deformation-induced part. Okay, this is something that we already have seen. No? Okay, here we always have the case of 1D Euler beam. Okay, so this is the model is always 1D Euler beam. Okay, in terms of constitutive information. So the displacement induced by the deformation, which is Wij as a vector, therefore becomes as Nij applied over Q F0I. Because again, if you go and check, so the overall position is the reference position plus the displacement induced by the deformation. So this times this is basically R0 over bar. This times this is the displacement for the element that we have called W, if you remember. Okay. While for the overall body, we name that U over bar. In any case, if we unpack the matrix N, we have this becomes C2 Ij, Psi ij, C1 ij, applied over QF 0i. Now, in the notes, you can also find, instead of QFI, QFIJ, okay? What is the difference in that? Is this wrong or not? It's not wrong. I mean, in our case, in our specific case, in which our body is constituted by one element, it's basically the same stuff, okay? So either one of the two is correct. This is correct in the case in which we assume that the body is basically consists of one element. If you want a more general treatment, in which you want to address a specific element within the body made of more than one element, you can add the J here. And this is actually what you find in the notes. Okay, but I mean, given that you make this hypothesis out, that you are considering a body consisted of one element, which I prefer to take in class because it is out the notation, but I mean, the concept is the same. The two, formulations are equivalent. Okay, so we can rewrite this in matrix form in the following way. So W1 prime, that's to say the derivative with respect to space, or order 1, and then we have W2 ij, which is a 2 times 1 vector, is therefore C2 ij, which is a rotation matrix in the 2D plane, so a 2 times 2 matrix. And then we have the following. We have Psi1 prime ij. And then we have the second row, which is Psi2. There are 2 times. So this is a 1 times 6. This is a 1 times 6. This is a 2 times 6 matrix. So this is the first row of the Psi matrix. Okay. Okay, derived with respect to this basically indicates this derivation, okay, first order derivative, while this is the second order derivative. First row, first. And then the second in the bottom. And then we have, of course, C1 ij, which is a 6 times 6. Why 6? Because we have 6 nodal coordinates. And then we have QF0i, which is a 6 times 1. Okay? So everything comes back together. So 2 times 1 vector. Yes?
Qui stiamo facendo le derivate di
W. Sì, vede, qui abbiamo W1 primo e W2 secondo. Perché a noi ci servono queste. Esattamente. Noi stiamo riscrivendo questa cosa qui, in cui c'è una derivata di ordine 1 sulla prima componente assiale dello spostamento indotto dalla deformazione e una derivata di ordine 2. Che cosa vogliamo fare? Siccome vedete che sono 2 quadrati, li andremo poi a esprimere come diciamo, una forma quadratica, quindi di un prodotto scalare di un vettore con se stesso. Ok, questa è una
forma derivata, ovviamente ci sono solo le psi che dipendono.
Esattamente, questo mi sembrava chiaro, no? Nel senso, quando io vado a derivare, so when I derive this, of course the only space dependent coordinates are in here, because here we have basically the angles. Here we have time, and these are the only ones that, in fact, this is actually what I was about to write. So let's make some room. So this is again. So we Psi ij1, sorry. So the first vector is something that we have already encountered. So it's the typical shape functions for the 1D beam. So it's something like this. Is at 0. And then here we have x1, 0, L, 0, and 0. Yeah, ij, of course. Okay, so this is the first row, 6 columns. And then you have the second part, which is this. We have 0. We have 1 minus 3 times x1, 0 over bar squared over L. And then we have plus 2 x1, 0 over L to the third. Then we have, so these are basically the same quantities that we wrote with xc, but then multiplying by L. So I'm making them explicit in x1, 0. And then we have x1, 0 over bar minus 2 x1, 0 over bar squared over L plus x1, 0 to the third divided by L squared, where L, of course, is the length of the element. Then we have a 0. Then we have a 3 applied over x1, 0 over L squared minus 2 x1, 0 L to the third. And then we have the last term, which is x1, 0 over bar to the third L squared minus x1, 0 squared over L, and that's it, ij, of course. Okay, it's always the same row. Good. Qui?
No, il secondo elemento.
Ah, sì. Esattamente, certo. Chiaro, sì, sì. Altrimenti dimensionalmente non torno. Okay, so this is just basically something that we have already seen. So we can rewrite everything in the following way. So this is the integral from 0 to L ij of what? Q F0 I transposed applied over C1 ij applied to what? C1 transposed C2 transposed, everything is transposed. So this is just C2 ij transposed. So everything here as well is ij transposed. So this basically continues here. I write it in the second row, but basically I'm just continuing writing. Then we introduce this matrix EA 0, 0, EI. This is the proper constitutive part, no? ij, always. And then here we have the same part, but not transposed. Okay, so you get what I'm writing? What I'm doing is this, just to be explicit. I'm writing this as the scalar product of two vectors, because you see you have two quadratic things, okay? And so instead of writing a scalar product, we are typically doing what we have done. So we basically write it as a matrix product with a transpose of the vector over the vector itself, okay? So this is what we're doing. So here now we have the same stuff, but transposed. That's to say we have C2 ij, then we have psi1 prime. Here I forgot prime. Huh? Prime here and derive 2 times here. Prime. No, there's no transpose. So we have 2 ij applied over C1 ij. And then we have, of course, again, QF0i. And all of this, if you want, we can write it like this, must be integrated in x10. Okay? Now we know that C2 ij transpose apply over C2 ij is the identity matrix, because this is a rotation matrix. So since here we have a symmetric matrix inside, what we have eventually is that multiplying this times this times this will produce the canceling out of the C2 matrix. You can try if you want. Huh? So basically what I'm saying is that the C2 matrix here vanishes. Okay? All right. So it becomes 1 over, U ij is 1 over 2. We bring out as usual, the quantities which do not depend on time, on space, transposed. C1 ij transposed. Everything multiplying the integral over Lij, over the length Lij, of what? Well, again, sorry, here we don't have to put it the transpose, of course, because we already wrote it in the row. So it doesn't need to be transposed again. So 1 prime transposed. Then we have 2 derived 2 times transposed, applied over EA 0, 0, EI, everything again, the superscript ij. And then we have this matrix here, 1 prime, psi2 double prime, ij, ij, in the x10, and then we have C1 ij and QFI f0. Okay? This can be rewritten as 1 over 2 QF0 I transposed KFF ij times QF0 I with KFF ij being defined as C1 ij transposed integral from 0 to Lij of what we have written before. So C1 prime transposed, psi2 double prime transposed, ij, ea 0, 0, ei, ij, and then again shape functions derived one time and two times with respect to x1. Okay, and this is the structural stiffness matrix of the element. Okay, so you see here we have everything, no? We have the constitutive, let's say, constants, and then we have the psi, which we defined. So basically, and then we have C1, which we have already identified. So everything here is known to get this. Okay. So you see here how we actually have implemented this case. So this basically closes this exercise. Now, I would like to start let's say the last topic of the course, which is, as I anticipated, the adoption of coordinate reduction techniques. Okay, so okay, so what are these coordinates reduction techniques? So these coordinate reduction techniques are procedures, methods that we follow to reduce the order of our models. In particular, they are typically adopted in discrete or discretized models. So what we are dealing with, no? For example, FEM models, FEM models. So typically adopted on discrete or discretized models. So discrete are those models which are naturally parameterized as discrete. Discretized are continuous typically, which have been discretized, for example, with the adoption of the restricted formulation. What is the outcome? The outcome of these the same methods are reduced order models. Which are in fact also known as ROMs, reduced order models. Okay, but what do they actually consist in? They consist in, as you can already imagine, introducing an approximation so that we can reduce the number of the variables, in particular of the nodes for FEM models, in our model, at the cost, of course, of renouncing to some information from the model that maybe we don't care of. So we don't need to take all the overall model. We can basically simplify, reduce it, retain the information that we need, and have a simple, faster, more, let's say, trustworthy model to work with. So in fact, let's say the adoption of these techniques that we will see in detail, the application is ideal in 3 cases. First, when we have an interest for the response of the system in a limited bandwidth of frequency. So we don't care about the response of the structure or the system on the overall spectrum. We only have to make sure that the behavior is what we want in a limited bandwidth, okay? So interest towards the response of the system in a limited frequency bandwidth. Okay, we will see why. Then typically, when the model is composed of multiple bodies, I think this is the case for a multi-body course. And then, when we have a body constituted of multiple parts, so that basically we want to condensate, if you want, some part of the structure that we don't really care of into the master part of the body, losing some information, but again, having a simpler model in the end. I know that it sounds abstract so far, but it will become more clear in a minute. Okay. Let's start off with the notation, okay? So that we are clear on what we are actually dealing with. So, say notation. We will adopt a simplifying hypothesis. We get rid of rigid motion. So we will consider a system in which there is no rigid motion. It doesn't really make any difference in terms of application, because eventually you can always reparameterize, as we know, let's say the coordinates, our variables, into a rigid part and a deformation part. So, but just for the sake of clarity, we, let's say, get rid of the rigid part. Okay, so again, it's only to simplify let's say the treatment, not just really to impose a limit on the applicability of the method. So, simplifying hypothesis. Simplifying hypothesis. No rigid DOFs, degrees of freedom. Okay? In this sense, we have that we will call our mass, structural mass becomes, we will recall it as M, so we drop the F if you want. But in theory, we are dealing with the MFF to this. No? Then we have the KFF. We call it K. And of course, the QF becomes our Q. Okay. So what is the basic idea of the reduction techniques? Well, it's very basic if you think about it. We start off from a vector Q of all the variables of the system, which has a dimension n times 1. And we want to pass to a vector QR with the subscript R denoting reduced, if you want, which has a dimension m times 1 with, guess what, m smaller than n. That's it. So this is the original. And this is the reduced model. And the idea is to express this through a relationship so that our Q, which is n times 1, is equal to a matrix R applied over the QR. This is m times 1, so this is n times m. Okay? So this is the reduction matrix. Okay, so this is in time. But we see that it's much more convenient to work in the frequency domain. The frequency domain, it basically stays the same. The only difference is that we write the following. Yeah. Like so. Check. And times 1. What are these? Fourier transform sign. We pass from the time to frequency domain via Fourier transform. These are Fourier transform. Okay, so we write it either in the frequency or in the time domain. Typically, we use the frequency domain. All right, so seems to be super simple, and it is, but it is super useful as well. Of course, in so doing, there are some hypotheses, so we cannot do it the way we want. The first hypothesis is that the kinetic and the elastic energy associated to the original system must be retained completely in the reduced system. So it means that all the kinetic, the reduced order model has to possess the same kinetic and elastic energy of the original model when we do the reduction. So, okay, we have to impose some this, so if you want, conservation of energy. So identity of kinetic and elastic energy between original and reduced model. Okay, so it means that U, which is the again, the elastic energy, in the original system, which we are used to write it like this, has to be equal to UR, which can be written as okay. Now, since we have that Q is equal to R over QR, we substitute it here, and we have what? This KR is equal to R transposed apply over K apply over R. Is it clear? I mean, I think it's pretty straightforward, no? And the same goes for the kinetic energy. So these are relationships that eventually will be useful once we have to determine R. So again, the implementation of a reduced order technique is completely identified by the determination of R, okay, which basically allows us to pass from the original set to the reduced order set of variables. So we need to define this. Once we have this, we can define M, we can define K, we can define everything that we need. So T, which is 1 over 2 of Qt dot times M times Qt dot, and that's it, must be equal to T reduced, which is, again, MR QR. Okay. Again, of course, these reduced order transformation matrix R, TV are non-dependent in time. That's why here, when I did the Fourier transform, it stays the same. So we can, in force of this observation, write also the following: that if this is true, when we derive it, when we derive this, you have that it is simply like this. Okay, nice. And of course, the consequence is apparent. So we can write that MR is, again, okay. Okay. Well, so this is the first hypothesis, if you want. No? Then we have a second hypothesis. So the hypothesis number 2 that we divide our vector Q of the original set of variables into a slave part and a master part. Master and slave. Okay. So we divide, or we partition if you want, our Q vector into a master part Qm, this is a capital M, and a slave part. Qs. so that our Q becomes written as such: Q master, and then Q slave. And in so doing, when we define and we choose which are the master and which are the slaves, we have to pay attention to one very important aspect, that no external load must be imposed, applied, acting on the slave nodes. So, no external load will have to be applied or to insist on slave nodes. Okay, so of course, as you can already imagine, the slave nodes are those that we will collapse, we will condensate over the master. So the slaves are all those nodes that we would like to get rid of. But when we choose the slaves coordinates on the slave nodes, we have to keep in mind that we cannot approximate nodes or parts of our system in which there are actual external loads acting on them. Those must be master. So we can, for example, if we are doing, for example, a static analysis, one smart move would be to consider a static equivalent distribution of forces and moments that acts on other nodes, so that we can eventually consider another distribution of forces and moments, and eventually basically move, if you want, the moments and the forces, so to be able to consider the nodes as slaves, if you really want to, for example. Okay? All right. At this point, what we do is to write down the dynamic equation of the system, which is super simple in this case. Which in the time domain, as we have seen for the structural problem, reads as follows: K, Q equal to QE. Here we are basically not considering contact forces, all the contact force, all the constraints are workless, blah, 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 blah. Okay, this is the simplest thing that you can actually find. Or in frequency, it becomes minus m overhead. In this case, as we know, m unfortunately depends on time. Q overhead omega squared plus k overhead Q overhead equals to Q E overhead. I hope that this does not seem to be strange. Second order derivative with respect to time, when you do the Fourier transform, you get minus squared the circular frequency. All right. So what we do is basically rewrite the last equation, introducing the partition between master and slaves, also in the matrices. And this is what we do. Yes, I think we're going to have some time to do it as well. So let's introduce our partition in the formulation. So basically what we get is the following. Let's actually just write it in the frequency domain, because this is eventually what we are going to be needing. Oops. So we have a minus here. You're going to have a round bracket. Here we're going to have an W omega squared plus another matrix, which is the K. Here. Everything multiplying what? Q M over bar and Q S overhead, sorry, equal to the vector of external forces. Now, on the master, we do have something that we write here as the vector F over bar overhead. What should I write here? Okay, 0. And here, well, we're gonna just denote them like this: MSS overhead, sorry, this is not MSS, of course. This is MMM, MS, SM, which is of course the same as SM because it's symmetric, and then we have MSS, and the same goes for K. Yeah, they all have the overhead. KMM overhead, KMS overhead, KSM overhead, KSS overhead. Okay, so as you can see, it's very simple. Now, let's rewrite this system in terms of two equations, because this is a matrix system. Let's write into two equations. So the system can be rewritten as basically a system of two matrices, of course. K M overhead QM plus K MS QS minus W omega, sorry, squared applied to M, again, MM overhead QM plus M MS QS equal to this phantomatic F overhead. And this we call equation A. The second line reads as follows. KSS equal to omega squared applied over M S M overhead QM, right? And then we have M SS QS. Okay, and this we call B. So this is the general part. Now is where we, let's say, make some assumptions and specify which kind of reducing order technique do we want to implement. The first one, which is the static condensation, also called Gaian-Iron method. Have you ever heard of this? No? Okay. Basically, assumes that we get rid, if you will see, of one part of the static, of the slave part. The dynamic part of the slave will be neglected as follows. So this that we are going to write is valid for the static condensation method. If you want, aka as the Gaian-Iron method. Gaian-Iron, from the name of the two engineers that developed it, method. What do we do is the following. We denote Q static, slave, sorry, as two parts, the static and the dynamic. Okay? So this is the static part, and this is the dynamic part. Okay? Of the slave nodes. Now, in the static case, in the static case, of course, omega is 0, no? The frequency is 0. And therefore, equation B reads what? If you go and check, it becomes Ksm times m plus Kss Ks of course here we only have Kss is only here we should have Qs, no? But since we are in the static case, we only have the static part. Okay, this is equal to 0. And therefore, from here, we can get that this static part of the slave response is minus Kss to the minus 1 applied over Ksm. In terms of the master, we also rewrite it as SS matrix. Okay, so I mean that this part here is this part here. Okay? Now, what we do is we rewrite equation B when W is not 0, so in the general case, using this matrix S. Okay? So we rewrite equation B for omega different from 0, making use of S. Okay, so we basically rewrite the second equation, just introducing this new SS matrix. And what we get so basically we substitute this QSS as SSQM. And we can get that QSD becomes KSS over hat minus omega W MSS to the minus 1, applied to omega squared, applied again to MSM minus MSS over hat times this SS that we have just found times QM. Okay? So basically what we did with the first part, with the first case, when omega was 0, we were able to express the static part of the slave in terms of the mass of the masters. We used this result in the original equation for omega in general different from 0 to express the dynamic part of the slaves in terms of the masters. Okay? Is it clear? Now, the founding hypothesis of the Gaian-Iron method is that we assume that this is 0. The dynamic part of the slave nodes is 0. When does this has sense? Well, saying that this is 0 means, indeed, from this definition, that this first part is very small. Assume that omega in general is different from 0. Okay. So assume that the first term is very small means that the part between round brackets is very large. But the part between brackets is the eigenproblem of the slave part of your system. So it means that you can use the Gaian-Iron method and therefore consider the dynamic part of the slave nodes as 0 when the dynamic of the slave nodes has frequency which are much larger than the bandwidth that you are interested into. Is this clear? If the slave part of your system has a dynamics defined by eigenvalues which correspond to frequencies which are much larger than those of interest, then this part is very big, the -1 is very small, and QSD is basically 0. Okay, so for example, you have a satellite with appendices, brackets and so on, which you want to condensate in the central part of your satellite. If the brackets have a let's say an independent frequency, so basically a mode shape which only involves the motion of these appendices, have frequencies so high with respect to the, I don't know, frequency that you are interested in, which can be 0, 15 versus, then you can do this method. And you can reduce, of course, the number of variables by a lot. By a lot. Okay? So we will write it here. The founding hypothesis of the Gaian-Iron method is to set Q as D equal to 0. But this, if you want, we can call this equation as star, okay? From star, you have the KSS minus omega square MSS is very large. But this, again, is the eigenproblem of the slave part, dynamics of the slave part. So if the dynamics of the slave part is characterized or has features, frequencies, say, to be more proper, natural frequencies. Much larger than those of interest, then we can assume that QSD is basically 0. Okay? And therefore, we have that Q, which is an n times 1 vector, which is typically divided into a master part and a slave part, we can rewrite it as identity matrix Here we have S, S. Qm. So this is again an n times 1. This is an m times 1. Actually, this is, yes, you can call it, well, typically, yeah, m times 1. And this is again eventually what? You see, this is exactly the relationship that we wrote at the first. So Q as a matrix applied to Qm. So this is the R matrix that we were searching for. This is R Gaian iron applied to Qm. So this, the reduction matrix of Gaian iron method. Okay? Which is again, this is the identity matrix. Huh? Okay? So we have derived the matrix that allows us to pass from the vector Q, which is n times 1, to the vector Qm, which is m times 1, with m much smaller than n, resorting to this matrix R, which is the reduction matrix of the Gaussian-Iron method. Again, we can apply this, given that there are no forces on the slave parts, and that we can assume that the dynamics of the slave part has natural frequencies which do not typically are included in the bandwidth of interest. Okay? All right, so this basically closes the lecture. So let's, I'm not sure if, okay, let's export this first. I think it's this one. Okay, so this closes the lecture. Adesso vi faccio vedere un po' di temi, di tesi, se siete interessati. È l'ultimo, diciamo, 20 minuti.